Hello, Geometry Honors. Today we're going to do our next to last lesson in Chapter 10 about circles and some interesting aspects of them. And today we're going to focus not on angle measures, but on segment lengths in circles. And so specifically we're going to be talking about parts of chords, parts of secants, parts of tangents, and it gets kind of interesting. So first things first, when two chords intersect in the interior of a circle, each chord is divided into two segments that are called segments of the chord. And the first thing we're going to learn about segments of chords is, the segments of chords theorem. And it says this: if two chords intersect in the interior of a circle, well, I'll say ... Let's draw a picture. So you got a chord C, D, intersecting with chord A, B at point E, we'll say. When you have that situation, two chords intersecting in a circle, then you're going to know that the chords are kind of split up sort of proportionally in a way, but specifically, if you have a chord split up, the product of its segments, AE, the measure of AE times the measure of EB, that is going to be equal. That product is going to be equal to the product of the other chords segments. So DE and EC. Which is kind of weird. It's kind of fascinating. And I do kind of hate just giving information and expecting you to believe it just because I tell you, but that's kind of what I'm doing here. I'm actually not sure right off what the proof is for it, so I do apologize. But that's the relationship right there. Chords intersecting, the parts of the chords, the product of those are going to be equal to each other. AE times EB is going to be equal to CE times ED. All right, so we got a little example here. So this is interesting. We got a lot of X's. And so, we just learned chords intersecting, then the parts, the segments of a chord, so x plus 1 times 3x is going to be equal to x times 4x. And let's see here. We'll have to multiply together. We'll get 3x squared plus 3x is equal to 4x squared. And looks like we got a quadratic, so there's a few different ways to solve a quadratic. There is square rooting, there's factoring, there's the quadratic formula. You could even graph it, find out where the graph crosses the x-axis. Those would be the solutions. Looking at this, I think I'm probably going to be able to solve this one by factoring. Probably be the most efficient way. So to solve by quadratic by factoring, you want to get it equal to 0. I'm going to move these over because when I do that, subtract the 3x squared, I'll get x squared. Subtract the 3x, I'll get minus 3x. And then I can factor a monomial out of x, leaving behind an x minus 3, and then I can do the 0 product property and get answers of 0 and set x minus 3 equal to 0, 3. But does it make sense to have a chord that has a measure of 0? Not so much. So I'm going to stick with x equals 3. Now, that's not my final answer. I should not have blocked it in because it turns out they want us to find RT and SU. So they want us to use this. So the measure of RT is going to be 3 plus 1 is 4. 3 times 3 is 9, so 4 and 9. RT is 13. 12 and 3. SU is, the measure of SU is 15. And there we have it. Those should have been blocked in. Okay, another relationship. Before I get ahead of myself, a secant segment is a segment that contains a chord of the circle and has exactly one endpoint outside the circle. So let's draw a picture here. So a secant segment is a segment that contains a chord of the circle and has exactly one point. So chord, but then it's got one point outside of the circle. So this is called a secant segment. A secant would be a line that slices through, but this is a secant segment. The part of the secant segment that is outside the circle is called an external segment. External segment. So what we've got here is the whole thing is called a secant segment. And just this part of it right there is the external segment. Okay, so another relationship about these different segment measurements is this. If two secant segments share the same endpoint, outside a circle. Let's draw a little picture here. So you've got a secant segment. Whoops, I drew an arrow, but did not intend to. You've got a secant segment, it stops. You got another secant segment that happens to stop at the same point. So if you got that sort of relationship, you got E, A will be the intersection there, C will be the intersection there, B is the endpoint here on the circle, D is the endpoint here. Then the relationship that exists there, now watch this, when it was inside it was partial times partial equals partial times partial. But when it's on the outside, the relationship is a little bit different. Then EA times EB is equal to EC times ED. So it's the external segment times the secant segment is going to be equal to the other external segment times the secant segment. So it's a slightly different relationship. So on something like this, it's going to be the external segment times the secant segment is going to be equal to the external segment times the whole secant segment, which in this case is 6. And we're going to have an equation that we can solve here of 3x plus 9 equals 24. And we can get that x would have to be 5. So it's a little bit of a different situation, isn't it? It's hard to keep these all straight, I got to tell you. You'll probably want to practice. And then on the back, we've got one other relationship. So if you have two tangents, they're just going to, if you have two tangents, they're going to form, we've already covered that one. If you've got two tangents to a circle that meet at a common point, they're going to be equal to each other. That kind of dunce hat sort of thing. But there's one other relationship where if you've got segments of secants and tangents, okay, so here we go. If a secant segment and a tangent segment share an endpoint, outside a circle. I should really do ... instead of colon, but you get the idea. So you've got a circle, you've got a secant segment. Actually, let me draw the tangent first. A tangent segment, and then a secant segment. E, A, C, D. Then how this is going to be set up is similarly to what we did earlier with secant segments. You're going to think of the external segment, EC, times the whole secant segment, so ED. That's going to be what you're going to use there, but that's going to be equal to the tangent segment squared. That's the situation there. So the tangent segment squared is going to be equal to the external segment times the secant segment. And those are the three relationships. So you've got the whole thing times the partial is equal to 1 squared. You've got whole thing times the partial is equal to whole thing times the partial. And then you've got partials times partials are equal. So there's 3 different relationships going on there. And we've got some practice problems. So on the next one, we've got a tangent segment on the outside here, so that's going to get squared. I'll knock that out. But then we're going to have 16 times the whole thing, which is x plus 16. And let's see here. So I think the way I would probably go about this is instead of distributing, I'd go ahead and punch that in my calculator and then divide by 16. So we get x plus 16 equals, I think it ends up being 36. I maybe better double check my memory there. Let me grab a calculator. So 24 squared divided by 16. Yep, that's 36. And then we subtract the 16, we'll get x equals 20. But that's not our answer. They want us to find AB. Oh yeah, so AB is just x, isn't it? So AB equals 20. And there we have it. Okay, so next up, we've got them intersecting on the inside. So that's going to be partial times other partial is equal to partial times partial. We'll get 20x equals 40, x equals 2, and we found the value of x. Okay, again, we're intersecting on the inside there. So we'll have x times x plus 1 is equal to 18 times 4, partial times partial. Looks like we're going to have a quadratic here, so we'll talk about how to solve that. So I've got a quadratic. If it was just x squared and no x there, I would solve it using square roots. But because there's an x there, I'm either going to have to solve it by factoring or the quadratic formula or graphing, or I suppose. So, but to do all of those actually, we're going to have to get it in standard form first. Standard form is in order of x squared, then x, then the constant equal to 0. So we'll have to subtract that 72 over. And then from there, we will, well, I think it's going to be factorable. So, yeah, I'll factor it. The full AC method is kind of a chore. But yeah, you find A times C, find the two numbers that multiply together to make negative 72, but add together to make 1 in the middle there. But when it's just a leading coefficient of 1, I kind of like to cheat a little bit. I know that it's going to split up into x times x. I really just have to worry about this negative 72 and what numbers will add up to make 1. And it turns out that it's 9 and negative 8. And then I'm done factoring. So that's the nice thing. You can factor really quickly if your leading coefficient is 1. If it was something else, the factoring would take a little while. You'd have to do the full AC method. You would have to factor by grouping and get your answer that way. But we're done pretty quickly here. Then we do the zero product property. Set x plus 9 equal to 0. Set x minus 8 equal to 0. And we're going to get negative 9 and 8. But the thing about negative 9 is it doesn't make sense in this problem because we're going to have a negative chord length, which is not possible. So it turns out x equals 8 is our solution. Moving on to example 6, we've got, so we've got two secant segments, don't we? So it'll be external part times the whole thing. That's going to be equal to the external part times the whole thing. And we just got to simplify this, divide the 40 over. I get 20 1/4. On example 7, we've got a tangent segment that gets squared. It's going to be equal to the external segment times the whole thing, which in this case would be 25. And I get x squared is equal to 225. And this quadratic's easy to solve because we just need to undo the squared. So square root it, square root it. Technically, we get plus or minus 15, but the only answer that makes sense in this case would be the 15. And now we've got them crossing in the middle again, so we're going to have partial times partial, so that's x squared equal to 8 times 16. So we'll get x squared is equal to 128. And then solve that by square rooting. Technically, we would need plus or minus, but we won't worry about that in this case. 128 is not a perfect square, but 64 is a perfect square, and 64 times 2 is 128. So the square root of 64 is 8, and our answer is 8 square root of 2. All right, so the practice for this is page 692, numbers 1 through 27, odd. Thanks for watching.